Hello, here are our solutions for the 3.7b practice set, number 20. What I've done already is gone ahead and set up all the problems, because that's what you were expected to do at least, and this way you can see what the setup looks like, and then we'll just take it from there. Alright, we're just taking from the very beginning and try to quickly go over all of them in a way that hopefully will help you understand how to get those answers. For the first one, we have this circular oil spill, right? So this hence the reason I drew this circle over here. We're given that dr dt is 1, and we want dc dt, where c is the circumference. So because I want the rate of change of the circumference, the equation I'm going to use is going to be the circumference formula, right? And then I need to find dc dt, so I take the derivative of the circumference formula, right? We're taking the derivative, and we do this. d dt of c is dc dt, right? This says the rate of change of c with respect to t. And then we take the derivative of the right hand side, which 2 pi is just a constant, so it's just stays out there, 2 pi. And then we take the derivative of r with respect to t, which gives us dr dt, right? And the thing that we want here is the dc dt. So I should be plugging in a bunch of stuff for everything else to get the dc dt. We know that dr dt up here, it said it was 1, so I plug in 1, and we get dc dt equals 2 pi. Then we just need to write the units, right? What is circumference measured in? Well, it's measured in this case, centimeters. And what is time measured in? In this scenario, the time is measured in seconds, so it's going to be centimeters per second. All right, number 2 here is the one that gave a lot of people trouble in class. We have a sphere. We're given dv dt. How do we know that's dv dt? Well, one, they're telling us that the helium entering the balloon is 3 cubic centimeters per second. Remember, volume is measured in cubic units, area is measured in squared units, and length is measured in just regular units, right? So it's giving me cubic centimeters, which means it's giving me a volume, and it's saying the rate of volume is cubic centimeters. Right, and what do I want? It says what is the rate at which the radius is increasing, so it wants dr dt when the volume is 54. So it's going to write this when v equals 54 pi over 3, right? It's telling me that when the volume is that, I want to know how fast the radius is changing. All right, so the equation we're using here, because we want dr dt and I'm given dv dt, I need a volume equation. So our volume is going to be 1/3 pi r squared. Oh, sorry, I'm doing cone. So we're doing 4/3 pi r cubed. This is the equation for a sphere. We want dr dt, so we need to take the derivative because there is no dr dt right now. So the way we get that is by taking the derivative. So we're going to take the derivative of our entire equation, and that's going to give us dv dt, right? The derivative of v with respect to t equals 4/3 pi is a constant, so it can kind of just sit over here. And then we're going to take the derivative of r cubed, which I'm going to take a few steps I would normally not take, but I'm going to write them here. Derivative of r cubed is 3r squared times the derivative of the inside, which is dr dt. Right, and then I can simplify this, and hopefully you can see that this 3 and this 3 are going to cancel, and so we'll be left with dv dt equals 4 pi r squared dr dt. All right, that is my derivative, and now I can try to start plugging in things I know. So I'm going to say, oh well, dv dt equals 4 is a constant, pi is a constant. I'm going to put r right there. I'm going to put dr dt right there. But this is where we encounter this issue of I don't know what r is. I know what dr dt is, right? I know this one, and I can go ahead and put that in there. I know I know dv dt. I want dr dt. Right, I want dr dt. So dr dt is going to go here. Let's go and highlight it because that's the thing I want. So I want dr dt. That's what I want. So I'm not going to be able to plug things in for that, but I know dv dt. So we're going to erase dv dt and go and plug in what we know, right? We know dv dt is 3. And it's positive because it's going up, right? But we need r. We don't know what r is. But we have an equation that relates v and r. Right up here, our original equation relates v and r, and we know v. So we can just go back up to this equation and plug in the volume in for the v, and now it's a single variable equation that we just simply need to solve. And I think the part of the thing that was like confusing for people is like, you know, multiplying by the reciprocal and dividing by pi and then cube rooting. It was a little bit confusing. So here's an easier way. Okay, so what is 54 pi over 3? Well, let's just pretend we're allowed a calculator, right? 54 pi divided by 3 is 56.54. Let's round it up to 9. Right, that is what 54 pi over 3 is. What's 4 pi? What's 4/3 pi? Right, let's do that now. What's 4 divided by 3? Actually, 4 pi divided by 3. That's 4.189 times r cubed. Okay, so now imagine how would I solve this equation? Well, I would divide both sides by this constant, right? Divide both sides by this. And that's going to give me r cubed equals 13.499. That's r cubed. How do I find r? Well, I take the cube root of both sides, right? We're going to take the cube root of 13.499. And we're going to get, if you don't know how to get the cube root on your calculator, you press math, and then you can see it as number 4 on there. So cube root of 13.499 is going to give me 2.381. So that can be my r. But again, that's not the answer, right? So maybe I shouldn't box it because that's kind of confusing to some people. I'm not going to box it. That is my r. The only reason I did all this is so I could put some number over here, right? So it's going to be 2.381. That's r, right? That's how I found that r value. And then again, like, yeah, there's some weird numbers, but it's simply like just do it on a calculator or something, right? So like let's go and put this into my calculator, right? 4 pi times 2.381 squared gives me 71. So I now have 3 equals 71.241 dr dt. And how do I solve that equation? Well, I divide both sides by 71.21, right? So it's 3 divided by 71.241, and we get 0.042. This is dr dt, right? This is my rate of change. This is not the exact answer because, you know, we rounded it off. We're using a decimal approximation, but it is helping us reduce that algebraic step, those algebraic steps that were confusing a lot of people. I do need to put a unit on this, right? Radius is measured in centimeters, and time in this case was measured in seconds, right? So it's dr dt, centimeters per second, and that's the final approximate answer for that one. All right. Alrighty, so continuing, we have the sphere. We're given that dr dt is 2 centimeters per second. We want dA dt, where that the area is the area of the cross section. And some people on this were confused about what a cross section is. And like if you actually look at like a sphere, like the sphere you drew or the sphere that's on here, you can kind of see that cross section is this little shape right here, which it doesn't look like a perfect one right now because it's, you know, we're looking at it at an angle, but you can, like, if you think about it, if I cut a sphere like that, what would the shape be? And then the answer is it's a circle, right? If I cut a sphere in any direction, really, I'm going to get a circle. So it's a circle with radius r. So the equation I'm going to use, because I want the area of that cross section, it's the area of a circle, I'm going to use area equals pi r squared, right? A lot of us are trying to use the surface area, but that's like the you know, the area around the circle. That's how much like wrapping paper, I would need to wrap it. That's not what the question's asking. All right, so I want that, and we want dA dt. So that means I need to take the derivative with respect to t. Right? How is it changing as time goes on? The derivative of a with respect to t is dA dt. The derivative of pi r squared with respect to t is, let me take a few steps here. Pi is a constant, so I'm going to have to ignore it right now. I'm going to take the derivative of r squared, which is going to be 2r, times the derivative of the inside, which is dr dt. And if I simplify this, then I will get 2 times pi times r times dr dt. Right? And, well, what do we want? Right? We wanted that dA dt, so that's right here. That's the thing I want. That's the thing I'm going to solve for. So I should be trying to plug in values for everything else, right? So dA dt equals 2 pi. R is going to go there. dr dt is going to go there. Which one of these am I given? I'm given dr dt. So I'm going to plug in dr dt here. dr dt is 2. But here's this issue again. I don't know what r is, right? So I have to use some sort of equation solving sense here to figure out what r is, right? I have an equation that relates a and r, my primary equation, but I don't know what the area is, right? I am given a volume, right? In the problem they gave me this volume up here. Maybe I should use that, right? So let's use this secondary equation, which is going to be volume equals 4/3 pi r squared. I know the volume is 36 pi, right? They told me that. And so I'm left with a single variable equation, right? Which, again, we could use the calculator method, but let's try something different. Okay, let's try to actually solve it. Let's do this first. Let's first multiply both sides by 3, right? I'm going to multiply the right-hand side by 3 and the left-hand side by 3, right? Those are going to cancel. And I'm going to have 3 times 36 pi equals 4 pi r cubed. Next, we're going to go ahead and divide both sides by 4 pi. Right? So, well, what's going to happen there? The pi's are going to cancel. This 4 is going to cancel a little bit with that 36, right? 36 divided by 4 is 9. And all of those guys cancel. So I'm left with 3 times 9 equals r cubed. 3 times 9 is 27. And cube root both sides, it's 3, right? What number cubed gives me 27? 3. So this 3 is going to go right there. Right? That's the whole reason we did that, is to find out what r was, right? And so now we have dA dt equals 2 pi times 3 times 2. That's 4 times 3 is 12 pi. What's the units? Area is measured in squared units. Centimeters are my length, centimeters squared. Time in this case is measured in seconds. So centimeters squared per second is the answer for that. All right. So there you go. Last one here is the oil spill. Something that confuses people on this is like, why am I using an R of 5? Well, let's think about it. It says we have an initial radius of 2, right? So when we first start, when time equals 0, the radius is 2. It's growing at a rate of 1 centimeter per second. That tells me two things. It tells me my dr dt, the rate of change of the radius with respect to time, is 1 centimeter per second. And I want to know the rate of change of the area after 3 seconds. So if we think about like what happens after 3 seconds, well, at time equals 0, there was 2, the radius was 2. After 1 second, it grew by 1, right? The rate of change of the radius is 1, so it grew by 1 to now being a radius of 3. After 2 seconds, it grew by 1 more, which makes it now 4. And after 3 seconds, it grew by another 1 more. The radius grew by 1 more, and it got to 5, right? So after 3 seconds, the radius is 5, all right? The equation we need here is an area equation, right? Area of a circle is pi r squared. We take the derivative of both sides, and we're going to get dA dt equals 2 pi r times dr dt. Right, notice that pi is a constant, so I do not need to use product rule. And we want the dA dt, so we're not going to be able to solve for that. dA dt equals 2 pi, there's the r, there's the dr dt, and we just plug in numbers there. So r in this case is 5 because it's after 3 seconds. dr dt is 1, that's how fast it's changing. And we're going to get 2 times pi times 5 times 1, which is 10 pi. Watt per watt, so it's dA dt equals, area is measured in squared units, right? So it's going to be centimeters squared per second in this case. All right, so that's that first page. I think I'll make a separate video for the other pages for people who want it. All right, so that's that for now.